Everybody, I'm going to talk about how to solve an NMR spectrum that is unknown to you and figure out what that structure might be. Keep in mind, this is it's a challenging process. It does take a lot of practice, but come at it with a bit of an open mind. Try to keep the frustration at bay and try to think of it as like an interesting puzzle that you're trying to assemble here. Hopefully you like puzzles. I really like puzzles, so I like them, but they're not for everybody. But again, takes practice. Don't be frustrated if this takes you a little bit of time to pick up on. Also, make sure you come to the study room if you have questions. We will be happy to help you. Okay, so when I'm starting off with a problem like this, typically this is kind of the order of events in which I do things. I start with the degrees of unsaturation, then I'm going to hop over to the IR. That's going to be a very fast little hop. The carbon NMR, also fast. And then I'm going to spend more time in the proton NMR and kind of like building those fragments and putting everything together. And then our final double check. Okay, so that's going to be kind of the main order of things. I'm going to try to keep myself organized here because I tend to go at it a little bit chaotically, but I'm going to try really hard to rein in that. And I have a table made already, so we should be hopefully good. Okay, so starting off with degrees of unsaturation here. So I am given a formula, which is pretty nice. Okay, so I know in that formula, I only have carbons, hydrogens, and oxygens, so I can just safely ignore the oxygens and think about my carbons and hydrogens. 2 times 10 plus 2. So first what I'm going to figure out is what is the number of hydrogens that I would expect in a saturated case, which is 22. Okay, since I have only 12, so 22 minus 12 divided by 2 is going to give me my degrees of unsaturation. So that's going to be 10 divided by 2 is 5. Okay, any single time I have 5 degrees of unsaturation, I'm just going to go ahead and write out my good old friend benzene right there. Okay, 4 or more is what we're looking for here to just kind of point us in the direction of benzene. Okay, so benzene has 1 degree of unsaturation in the ring, 2, 3, 4 from all of the pi bonds. Total of 4 degrees of unsaturation just in that one piece. Okay, so anytime I have 4 or more, I'm going to be pretty suspicious that part of that is going to include a benzene ring. So I usually just draw it up so that I have it in front of me. Okay, next up, we're going to look at the IR very briefly here. So the IR, the very first thing that's popping out is this kind of broad, weirdish peak over here. And because I have oxygens, I'm going to think maybe like alcohol, right? That's kind of a reasonable guess. All of this stuff looks kind of like what I would see with the sp3ch. So is that the most helpful thing in the world? Not really. Is it possibly obscuring some of the stuff that we'd be seeing from the benzene in terms of the sp2ch? Yeah, probably. We're also told the 1678 and the 1607 wave numbers. Okay, so this one and this one. So that 1678 is pretty close to the carbonyl region, and my 1600 is pretty close to my CC region, okay? Which, again, this is more confirmation telling me benzene. And this is kind of my first indicator that part of this oxygen mess that I've got might be including some sort of carbonyl group. Now, you can dig through and look at those numbers on the IR thing and dig through to find a little bit more detail on what the carbonyl is. I usually don't bother with that because I find it in the NMR. But the IR is helpful in just telling me, look for a carbonyl and don't ignore that. Okay, so then let's go ahead and move on to our carbon NMR. So we're looking right here. We do have a summary provided, so we've got that as well, just to kind of double check ourselves. Important to note that when you're running NMR experiments, you have to be dissolving your analyte that you're trying to look at or whatever sample you're doing in a solvent. and that solvent is going to show up in your NMR. Okay, so in this case, this peak is solvent, and this peak is also solvent. Okay. Also, as you are doing NMRs in lab, keep in mind that if you have anything like acetone, ethyl acetate, any of those kind of solvents in your sample, they will also be showing up in NMR. So I would highly recommend you watch the solvent table video to see how to identify those, because there is a very nice table that shows you where everything is. So those are the two. In this case, it was taken in deuterated chloroform. So it's a singlet at 7.26 in proton NMR. And it's I hesitate to even say triplet. It's kind of a triplet at 77. It's not a real like triplet just because it's all like, let me try that again. It's 3 even peaks, so it's not the same peak height that we're looking for a triplet. But that's something to look for. You're going to use deuterated chloroform a lot in lab. Okay, so in our carbon NMR, I'm looking at number of carbon peaks first. So 1, 2, 3, 4, 5, 6, 7, 8. Okay, so that's telling me that there are 8 unique environments. If I, again, look at my formula and the fact that I have 10 carbons here, that means that I have to have a couple environments that have more than one carbon involved. Okay, so I have to have some amount of symmetry here because that number of peaks is smaller than the number of my carbons. Okay, so I know that I got symmetry. Then I'm looking for just kind of big chunks of information here. So I've got some alkyl carbons. I've got one carbon that's in the CO, C electronegative region. I'm just going to keep it as CO though, because I know that the only electronegative atom that I have access to is oxygen based on my formula. Over here, I have my aromatic region. And we can see that pretty nicely just because we have our degrees of unsaturation. We've got that benzene kind of poking out at us in the IR. So we know to look for it. We're kind of already tuned to look for these things. When I'm looking at the aromatic region, it's pretty common to have a little bit of shuffling in and out of each side of that range, depending on what kind of things you have attached to your benzene ring. But keep in mind, because of the ring and how the symmetry on it works, it's going to be fairly common to have 4 carbon environments on your benzene. Because, for example, if you have a monosubstituted benzene ring, that's going to give you 1, 2, 3, 4 carbon environments there. If I put another thing over here, I'm still going to have 4. If I have something there, I'm going to have 3. But 4 is pretty common. 5 would be really weird. Okay, I don't know if I've ever seen a 5 because I just don't think it would work out. Okay, so that's my aromatic region. So that means that this little guy over here is in my carbonyl region because it's not super high, like 200. It's not a ketone or an aldehyde. So we're thinking about ester or carboxylic acid. And I did not include amide in that list because, again, we don't have a nitrogen. So I'm not even going to consider it. I'm going to be following that molecular formula that we were given. Okay, so that's my carbon NMR. We're ready to head into our proton NMR. Okay, so the proton NMR, we can start off kind of thinking about the number of peaks as well. So we've got 1, 2, 3, 4, 5, 6 peaks. Okay, I'm just going to go ahead and label them. so that we can just keep them straight as we're discussing them. Again, that solvent peak right there, we're not going to be considering that as part of our molecule. So it also was not integrated, and it's just going to be kind of ignored here. So now I'm looking at that, looks a lot like a doublet. The B also looks like actually, let me do this in a different color. B also looks like a doublet. C is kind of a broad singlet. And what we're looking for there with that broad singlet, it just has pretty far baseline, kind of like there are split peaks, but it's not split, right? So that's what's telling us it's a bit of a broad singlet. Over here on peak D, we've got a triplet. E has a lot going on. So it's a little bit hard to count, but we can kind of count 1, 2, 3, 4, 5, 6. So maybe a sextet, and then F is another triplet. Okay. This is also written out in our summary, and it is shown that we have a broad singlet at that 6.5. Okay, so I went and put all this into a table already so that we can go and fill in this table and start drawing and building out some fragments. So if I've got a multiplicity of a doublet, that means I've got one neighboring hydrogen. So this is also going to be one there. Broad singlet, that's going to be an unknown number of neighbors. Okay, the reason it is unknown is if it is broad, it's that broadness is going to be kind of erasing any of the splitting that you might be seeing. So you don't really want to come in with any, if you have a broad singlet, you kind of just want to say like, I'm not sure what the neighboring situation is going to be like here, and just coming in with it where it makes sense. Okay, so that's our little note. Okay, don't use the fact that it's a singlet. It might be tricking you on that. But generally with broad singlet, we're thinking about OH. Okay, it's generally going to be some sort of acidic proton that's doing a lot of exchange with the solvent. So it's kind of appearing and then disappearing, and that's leading to that broadness of the peak. So it is helpful to just kind of note that, yeah, it's probably an alcohol. And we saw an alcohol peak in our IR. So that's, again, two pieces of information that are coming together with each other. Okay, so then our triplet for our 4.3 peak is going to be 2 neighbors. The sextet is going to be 5 neighbors, and the triplet, again, another 2 neighbors. Okay, so I'm starting to kind of build some stuff out. I can think about my integrations. Again, thinking back to our fragments video, if we're looking at something that's a chemical shift in the 8 to 7 region and we're integrating to 2, it is probably not going to be a CH2. Okay, it would be very, very hard for a CH2 to be in that chemical shift region because those are both aromatic. And because they're aromatic, you're not going to be able to get a CH2 on a benzene ring without breaking some octets. So we're probably looking at 2 CH groups for both of these. Okay, and they have to be in identical environments to be giving us that integration of 2 to make sure that they are lining up and saying like, yes, we are both the same and we equal 2 as our sum. Okay, for our neighboring H, we have next to a CH. Okay, for both of those. When we're looking at this one, if we remember our little note down here, this is probably just our OH. Okay, it's that broad singlet. It's telling us this is probably the alcohol peak because it's broad. So just think about this as your OH. And then that's kind of its piece. So the 4.3 peak integration of 2, that's very likely to be a CH2. And it is a triplet, so it is next to a CH2. Okay, again, as our most likely version of this answer. 1.8 integration of CH2, probably another CH2. It's a sextet, so it's got 5 neighbors. The easiest way to get to 5 is a 3 plus a 2, because again, we're thinking in those CH, CH2, CH3 kind of pieces. So it's probably next to a CH3 and a CH2. Okay, and then the 1.1 peak that is integrating to 3, most likely a CH3. It's a triplet with that means it has 2 neighbors, so it's probably next to a CH2. Okay, so if we think about building out our fragments now, I'm actually going to be putting kind of all of our aromatic fragments. I find it to be really annoying if you're trying to draw in fragments for a benzene ring, and you're trying to do like this type of move where you're not actually drawing the whole thing. I find that to be very obnoxious. So what I like to do is I like to think about the ring as a whole, because if I've got stuff in that aromatic region, I'm probably dealing with a benzene. We're not going to really be giving you stuff outside of that. That's a little bit nuts. But I'm immediately starting with that. And what we're looking for is what is the substitution pattern on this benzene that will give us 2 doublets that integrate to 2. Okay. And that's what we want to be looking at. So if you're really familiar with your substitution patterns, whether the ortho, meta, para, that's kind of what we're looking at. Very importantly as well is looking at what the sum of that aromatic region is. Okay, so I'll do in green. Okay, so for our aromatic H's in total, we have 4 H's. Okay, when we're thinking about that, we immediately want to be thinking about benzene as a structure has 6. Okay, so if I only have 4 H's, that must mean that I have 2 things on that benzene ring. Okay, otherwise referred to as a disubstituted benzene. So if I know that it's disubstituted, I have only a few options here. Okay, I could have the two things on my benzene ring getting me to sorry, the 2 things on my benzene ring being identical is one option. So whatever it is, but they're both the same. I could also have those same substitution patterns, but having the 2 substituents be different. Okay, so I've got the 2 options there. What I want to be thinking about is which one of these 6 options is going to be the one that fits my data the best. Okay, so what we can use here is we can use a combination of the proton data as well as the carbon NMR data, because as we talked about in the equivalence video, when we're looking at our planes of symmetry here, we're going to be ending up with different numbers of carbon environments. So sometimes going there and starting at looking at that is going to be most helpful, because that one has 3 carbon environments. This one is going to have 4. This one is going to have 2. Okay, so that's going to be pretty quick in terms of kind of helping us out with that. When we're looking at our aromatic region, we've got 4. Okay, 4 carbon environments in the aromatic region. So we know it's not this. We also know it's not this. For these two, they both have 6 carbon environments because we don't have any planes of symmetry, so we know it's not them. Okay, so just kind of process of elimination, we've gone from 6 to 2 really quite quickly. Then if we take into account our integration and the multiplicity in terms of what's happening with the proton and with the protons, right? If I'm looking at this plane of symmetry, I have 1H here, 1H there, 1H there, and it would be 1 to 2 to 1. So I would expect to have 3 peaks in my proton NMR for that meta substituted compound. If I'm looking at this one, that I only have this plane of symmetry, I've got 2 H's there that are the same and 2 H's there. There's only going to be the 2 proton peaks. It's only going to be splitting with each other. And we've got the 2 environments, okay? So that is going to help us get to the full elimination process there, where I'm just going to move these off to the side. Okay, where we get to that single fragment for our benzene ring. Okay, without too much work, mostly just counting things. And it does take a little bit of practice to get used to kind of knowing where your lines are or kind of cutoff points. Okay, so that fragment is done. We have an alcohol at 6.5. So if we just review real quick here, our kind of special functional groups or approximate proton chemical shifts. If we're looking at our alcohols, they're down here. A regular alcohol is like 2 to 5, and one on a benzene ring, so making a phenol, is 4 to 7. If I've got one at 6.5, probably in that 4 to 7. So that tells us a lot here because we can think about just saying, okay, well, I probably have that alcohol as one of my groups, right? So I'm already starting to build onto this initial fragment with the next pieces, just based on my chemical shift, okay? All right, so then my 4.3 peak, 4.3 is definitely in that kind of alpha to oxygen. And again, I'm picking oxygen here because we have oxygens to work with. So in my fragment here, I've got a CH2 and it's next to another CH2 and it's alpha to an O. So I'm going to start with an O and then put a CH2 next to it and put a CH2 next to that. And I don't know what's happening over there. And I still have another bond for the oxygen that I have to figure out where that's going still. Okay. So I've got that. And we know that this piece cannot be connected to that oxygen, otherwise we would be erasing that proton, and we definitely have evidence that that proton is there. Okay, so then 1.8, at this point we're pretty much in the alkyl region for both of these peaks. So we're not expecting them to be super close to anything super electronegative. So something to keep in mind as you're building your fragments here. So it is a CH2, so I'm just going to start with putting a CH2 down, and then it's next to a CH3 and a CH2. I find it does kind of help to just kind of mark them down. So whether you are highlighting them or drawing them in or both. Okay, I think it helps just to kind of keep yourself straight in terms of saying this peak is these protons because you're ending up adding more for your fragments. So I have those two. Let me just double check myself here. It's a sextet, so I've got 3 plus 2 neighbors, and I don't know what's happening over there. Okay, we're looking good. All right, and then our last fragment is a CH3. So I'm going to start off just with my CH3, and it's a triplet, so it's next to a CH2. and I don't know what's happening over on that side. And that's going to be the peak or the protons that are actually making that peak. Okay, so now I have my fragments. So I'm in a pretty good spot here. I'm starting to see how some of these things are kind of combining on each other. Because, for instance, I've got a methyl here, which is probably that methyl, because I'm looking for a methyl next to a CH2. That methyl is next to a CH2. So I've got some fragment overlap. I've got some chain situation happening here where that CH2 needs to be is next to a CH2, and I've got that going on, right? I've got my alcohol is probably on my benzene, and then I have to figure out what the other thing next to it is. And these are the fragments from my proton NMR. But again, we can't forget about the carbon because at some point we said probably ester or carboxylic acid with our carbonyl here. And when we're looking at that, like I haven't added any ester or carboxylic acid in these fragments, but I have things that could be like getting towards that, right? So if I'm looking at this fragment, that one is pretty suspicious in terms of maybe we've got an ester here. Okay, the other thing that's not telling me carboxylic acid is I would expect that in our IR, it would be like huge. They're really, really big. So if I'm not seeing that, I'm also not seeing a peak way down here in my proton showing me that OH, which sometimes those are hard to see because they are so acidic, but I'm not seeing any of that. And I am seeing this OR group, which has to be separate from this OH group. So that's something to consider, that this is probably telling me about my ester. Okay, and then I know in that ester, I basically have that as another fragment. Okay, so I'm going to add that to my fragment list as a fragment from my carbon and my IR. So at this point, we need to try to put it all together and see what happens. So we have a pretty nice start here where we have an end and then we have one kind of connection point. So I'm going to start with that fragment. Okay, so I need to figure out what goes at that connecting point. And when we're looking at what to put next, we really are needing to look for something that has multiple connection points to it now, right? So for instance, if I just went and plunked that piece on and just said CH2, CH3, done. Okay. At this point, unless I start messing with the fragments that I've already generated here, this is not matching the molecular formula that I was given. So if I go in and put something down that only has the one connection point, I'm going to find myself at a dead end, basically, where I've blocked myself into a corner and I can't do anything to change it. So that's not very helpful. What we want to be thinking about is adding it to pieces that have more than one attachment point included in them still. Okay, so in terms of fragments that I've got left that have two pieces, I've got this one and I've got this one. Okay, so if I think about this oxygen is probably going to be this oxygen, I can think about connecting either side of that to my benzene ring and just seeing what that looks like. And I'm gonna see how this works out, but I'm gonna try to do a progression here. Okay, so we can have one of those two options, essentially. So if I'm looking at my other fragments and kind of thinking about what I want to do next, the thing that gets me really messed up here is this piece. Okay, If I have this oxygen that needs to be next to a CH2 that's next to another CH2, I can't do that here, right? I'm basically stuck and I can't be including that kind of piece. Because if I put a CH2 here, that would be a different chemical shift than what I'm seeing with that 4.3. And just to kind of make sure that you're following along here with what I'm talking about, we're talking about the difference between that type of proton environment where we're alpha to a carbonyl versus this proton environment where we are alpha to an electronegative atom. Okay, that's going to be more downfield than the alpha to carbonyl where you're just next to a delta plus carbon. So that's the difference there, is that this doesn't give me the chemical shift that I need. Of my 4.3. Okay, that alpha to carbonyl would be much more upfield than that. So that means that this one is looking to be a pretty good option. I'm actually going to swap these so that I can continue on in my little progression here. Okay, so I've added my ester group here, and I'm just putting stuff in all of the gaps that I identified. So now, if I'm following on with this oxygen, I'm putting on this next piece. So I've got a CH2 and a CH2. Okay, and then I have another connection point that I need to deal with, but I've got those two carbons in there. And then we're coming down to our last two alkyl pieces. And what we want to be thinking about here is we're at the stage where we really need to be counting things up and seeing where we're at in terms of our formula. So I should have 10 carbons here. So 6, 7, 8, 9, 10. Okay, so if we're looking at this kind of sequence of events here, we've got CH2 and another CH2 and a CH3. So if I just make that last point a CH3, I have all the carbons that I need. I've got my 5 degrees of unsaturation. I've got 1, 2, 3, 4, 5. I've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 carbons. I've got 1, 2, 3 oxygens. I've got all of the pieces here. So once you have your guess, then you need to get into your check. Okay, really, really important that you go through and check to make sure that this data makes sense and that you didn't accidentally erase something and get rid of a connection point because you put together pieces that didn't have enough kind of open spots in them. So I'm going to take this structure. I'll try. Copy. And I have another copy down here. And we're just going to go through and make sure that we can assign the peaks here and that all of that data makes sense. Okay, so I'm going to go and label these again. A, B, C, D, F. Okay, so I've labeled my proton and my carbon. I'm actually going to change the carbon ones to a different color real quick. Okay, so I'm going to start with carbons. Why not? Sure. Okay, so my first carbon, the one past 160, that's going to be indicative of my carbonyl. Okay, so carbon 1 right there. By the end of this process, I should have all of this labeled with these letters and numbers. And I'm going to get myself another copy so that I don't have to do it all over same stuff. Okay, so then I've got carbons 2, 3, and 4. Oops. I definitely missed one. 3, 4, and 2, 3, 4, and 5. There we go. 8 is what I should have. Okay, so 2 through 5 is going to be all of our benzene carbons. Okay, one little trick to be thinking about here in terms of carbon NMR, you can't technically do integration, but you can do kind of like a fake integration where carbons that are about twice as tall. It's probably 2 carbons in that environment. Okay, if I have a really, really short carbon peak, we probably don't have any hydrogens on it. Okay, so that kind of helps us narrow things down a little bit when we're thinking about assigning our benzene carbon environments here. Because my 2 and my 4 are significantly smaller than 3 and 5. I expect to have one plane of symmetry here, so I have some of my carbon environments are going to be 2 carbons in each environment, but then I've got a couple that don't have any H's and are only 1 carbon each. So then I can narrow it down and say like 2 and 4 is probably these. If I'm looking at what they're connected to, I would expect to see that carbon being connected not only as part of a benzene ring, but on an oxygen. That is going to get us more of a downfield pull. So then this is going to be my 4. And then when I'm looking at 3 and 5, I usually don't worry too much about about differentiating there. But what you can do is you can think about the resonance that's happening and think about the fact that if I'm donating electron density in with that oxygen lone pair, I'm putting delta minuses on those carbons. And then same thing over here, if I'm thinking about withdrawing electron density, I'm going to be putting delta pluses on those. And that can kind of help show you your shielding and your deshielding, where this carbon is getting a little bit more shielded. So that's probably going to be my 5s. And my delta plus is getting more deshielded, so it's probably going to be my 3s. Okay, so a nice little way to use resonance there. Then I'm going on to carbon 6, which is in the CO region, so that one's pretty easy. And then we're going to see 7 and 8 just kind of step away from that electronegative atom in terms of their upfield nature. Okay, so all of my carbon atoms are assigned. It all makes sense. We all have kind of the numbers that we would expect. So if we're looking at the proton NMR here, if we start again from the left, I've got my 2H doublets. So again, we can be thinking about a similar situation here with our alcohol donating electron density and shielding, our ester withdrawing electron density and deshielding. So my most upfield is probably going to be B, which is going to be close to my OH. And then A is going to be the other ones, and that's going to be the same on this side. The next one is C, which is my broad singlet. So that's going to be my alcohol. And then 2H around 4, and that is a triplet, is going to be my alpha to O. That's a CH2 next to another CH2. And then I've got a CH2 that's a sextet. So I have 5 neighbors, and that's going to be E. So I got my 5 neighbors integrating to 2. And then finally, F is going to be my methyl group. So it integrates to 3, and it's got 2 neighbors, so it is a triplet. So all of it's matching out pretty good. I can assign all my peaks. None of them are looking super wild or anything. And that's the kind of double check that you want to be doing at the end. All right, so I know that was a longer one. If you made it all the way through, good job. But again, this is going to take practice. It's going to take a lot of time to kind of get used to things here. Keep asking questions, and we will get through it. And hopefully you enjoy solving some NMR puzzles here. All right, have a good one. I'll see you later.